Hello, everyone, and welcome to this webinar, Best Approaches to Solve the Reply Code Challenge 2023. We held on March 9th. During this session, you will go through the best techniques on how to solve the algorithmic problems that we proposed during the Teen Edition challenge dedicated to our external community, and the 101 edition dedicated to our internal communities. Let me introduce you our trainer for today, Gaspare Ferraro, here with me. Hi, Gaspare.
Good morning, everyone. Hi.
Hello, are you ready for this webinar? Okay. As I mentioned, this will be another learning opportunity for you since we hosted the Reply Code Challenge on March 9th. It's been a while already, but learning chances never stops. So we would like to propose you this first training session dedicated, as I've already mentioned, to the algorithmic problems. Let me give already the word to Gaspare, which has a lot to teach you, actually. Let me also remind you that you can use the chat on our video platform for our colleagues that are following us, or the chat on the YouTube channel to ask all your questions and doubts you may have. Our trainer Gaspare will try to follow all your questions and answer them. And in the end of the webinar, we will have also a dedicated Q&A session for you. So enjoy this learning moment, and Gaspare, up to you.
Thank you, Alessandra. So good morning to everyone. This will be not a lecture, but will be a live coding session. And in particular, we will see how we will solve the solution, how we will solve the challenges of the Reply Code Challenge we held in March of last month. We will start from the first task, and then we will go on the second and the third and so on. We will do not a lecture. We will not try to understand things in theoretical part, but we will all analyze the solution in practice. So we will start with an empty solution. We will read all the problem statement, and then we will try to write a working solution. So in my desk, I have prepared some input files, some output files. We will read the problem statement, analyze it step by step, and try to come up with a working solution in the easiest way possible. We will try to understand the easiest solution for each task, and then we try to optimize in order to solve completely as we are in a live challenge. So, if you ever participated in the last Reply Code Challenge in March, in the algorithm car part, we had 5 different tasks of increasing difficulty. We had a first task named car racing, and it was a simulation. It was an easier one in order to start with the competition. Then we have a second task called slot machine, which was a greedy approach. We had a first task named flowers, which was a binary search over the solution. We had a fourth task named miner, which was a dynamic programming task. And the last but not least, the buildings algorithm, which was a branch and bound approach. So I have already spoiled you the techniques to solve the challenges, but if you don't know simulation, greedy, binary search, and other terms, we will see in a moment. So the tasks are increasing order. I remind you that in the Reply Code Challenge, we had 5 different tasks of increasing difficulty, but also each task has 5 different levels. The first level of each task was prepared in order to be as simple as possible, and the last level was meant to be the difficult as possible. So in order to consider a task solved, we need to solve all the levels of the single task. Pay attention that different levels can mean different solutions. So a solution that works for the first level doesn't mean that works also for the second, for the first, and so on. This is because when we create a task, when we create an algorithmic task, we think that different solution exist for a certain problem, but we also want to everyone to participate with different capabilities. So if you are a beginner, if you are a novice in the coding challenge, we can easily solve all the first level of each task. And if you are a pro of coding challenge, you will be challenging by solving all the last level for all the proposed task. So we will directly pass the first problem. So we will give a brief introduction for the task. So each task is divided by a statement and a goal. We will pass the problem statement in PDF, so the original one during the competition. In the first challenge, we have a group of drivers that competes in a qualifying race, where a number of cars will race in a track, and each of the cars has a set of technical characteristics. So, for example, each car has a speed, has a turbo boost, has a time of the boost is active or not, and so on. And we also have the number of cars, the length of the track, and all the information. And our goal is to calculate which vehicle will complete the race first. So we want to find the winning among all the cars. Bearing in mind that each driver, of course, will do their best to win. So we will consider that all the drivers are competing in the best way possible by activating the turbo boost and all the speed of the race or of the competition as possible. The idea for this first simple task is simply find the fastest car by simulating the race for its competitor. So to solve this is enough to simulate step by step all the cars in the race. So we will see later what does it mean. But for this, it's simple enough to run a simulation. And this is, it's called a complete search. And this means that we perform a complete search over all the racing car. Back to the problem statement. So this was the real problem statement during the code challenge. We know that a group of drivers competes in a race, as I said before. We have a number of cars C and a track of R meters long. And each of the cars has a set of technical characteristics. So in particular, we have the identifier of the cars. So each car is a number, like in real life, starting from 0. So we had 0, 1, 2, 3, and so on until C-1. We have the normal speed of the cars in meters per second. So this means that the first car runs at 10 seconds per meters each second. We have a turbo speed. So this means that if you already play some racing game on console or computer, you know that it is possible to activate some kind of turbo speed, like the NOS, for example. And this also is measured in meters per second, which means that normally the car starts as a speed of C of S, and if you activate the turbo speed, will reach an higher speed of C of T. Of course, you cannot always use the turbo speed because otherwise it was too easy. So the normal speed doesn't make sense otherwise. And in fact, we have two other numbers. The first one is the cooldown time. So this means the amount of time in seconds we need to wait in order to activate the turbo boost. So you can use the turbo speed a certain amount of time, in particular the number C of T. So it means that each car has a duration time for its turbo speed mode. After that, you need to wait a cooldown time in order to activate again the turbo speed. So you have normal speed, you can activate turbo speed, you can use it for a certain time, and after that the turbo speed will deactivate, and you need to wait a certain amount of time to reactivated during the competition. So the race takes place in rounds, so it means that each second all cars make one step in advance. So this means that each car will instantly advance at its current speed. So for example, if the first car has a speed of 10 meters per second, after 1 second it will reach 10 meters. After 10 seconds it will reach 100 meters. So, as said before, each car has a normal speed of G of S and can activate a turbo speed of C of T. Of course, every contestant, every drivers will do their best to win. So this means that when the turbo boost will be again activated, they will use it. And then we use it for all the amount of time possible. Some classification. So we can read that every car will start with a fully charged and ready-to-use turbo boost. So this means that we can start the competition. All the drivers will start the competition with the turbo speed activated, and they will be activated after the duration time of each cars. After reading the problem statement, we need to understand the technical requirements of the task. In particular, we are described the input data and the output data, and we have some constraints in order to understand the size of the track, the number of cars, the number of speed, and so on. And we have, as I said before, the scoring system. So we have 5 different levels. Each one has increasing difficulty. So, for example, in the first level, we have only 5 cars. In the last level, we have 500 cars, and so on. And this means that the first solution can be brought with a naive approach, and then we need to optimize it in order to solve the last level. We have here an example in order to better understand. So in the first example, this is an example comprising 2 different subtasks. So this is the one and this is the second. In the first example, we have 2 different cars. Okay. And the first car means that, for example, it has a normal speed of 1, and the second car has a normal speed of 1. Then the first car has a turbo speed of 5 meters per second, and the second car has a turbo speed of 7 meters per second. And then each of them has a duration cooldown of 2 seconds, 1 second, and 4 seconds, and 6 seconds. In this example, we can see that the first car will reach 5 meters after 1 second, 8 meters after 2 seconds, 11 meters after 1 second, and 16 meters after 4 seconds, and so on. And we can see that the turbo speed is activated only once 3 seconds. So we have turbo speed activated instantly, and then we need to wait 2 seconds to reactivate the turbo speed. So we have turbo speed, normal, turbo again, normal, and the race is finished at this step, because after reaching the 22 meters, we already finished the track, because the track is long 20 meters. And this is the same for the second car, and we need to understand the amount of time for each car in order to pass the finish. And we need to find the ID of the cars with the lower time to reach the goal. So we will start directly to try to implement the solution. So I will split the page here. So for the code, I will use Python, but every language is okay. It depends how you are familiar with a particular language. So I will try to comment step by step in order to follow even with different languages. But if you have any question, please ask in the chat or interrupt me. So this is the base for each task. So we need first to read the number of test cases. So each input file is detailed by a set of test case. Each test case is in the same format of the others. So we need to find the solution of T different independent instances of the problem with the same algorithm, of course. So we need to read the number of T. After the number T, we need to iterate over all the possible test case, and we need to print the solution in a particular format. In particular, for each of the test case, we need to print the identifier of the winning car. So for each of the solution, we need to print a string in this format. So as we can see in the example, we have case 1, the solution is 1, case 2, the solution is 2. So the important thing is, of course, the solve function. So we have an empty function we need to write in order to solve the task. And the solution can be divided by the input reading, the simulation part, and the returning of the solution. So we need to read some from the standard input. So we had a number of data from the input file. In particular, as we can read from the problem statement, we had that, let me zoom it, okay. We had that in the first line of each input in each test case, we have a line containing 2 integers number, in particular the length of track in meters, and the number of cars. So first things to do is to read the 2 numbers R and C. So this can be done by first read the input. So this read the first line. We need to split the line by space. So we perform this operation. And this means that we take a line, we split in 2 parts, the first containing the track, and the second the number of cars. And these, pay attention because these are strings, these are not numbers, and we need to map to integer these 2 strings. In this way, we have read the 2 numbers in the first line. After that, we have C lines, 1 for each car, containing 5 different numbers. Each line will contain the characteristic of the current cars, and in particular, we had the car identifier, the car normal speed, the car's turbo speed, the car turbo speed, the cooldown time, and the car's turbo speed in duration time. Each of these 5 numbers are integers, so we need to perform the same things here, but with the parameters. And we have to do another for loop in order to read all the C lines. So we do this for E in range C, okay? And we read the numbers in this way. So CID, C of S, C of T, C of C, and C of T. We need to solve to store this number in a vector. So we need to allocate a vector here. Okay, we have an empty vector containing cars, empty array that will contain cars info. Okay, and here we have to push and to append all the information in the array. So we take these 5 numbers and append on the cars array. Okay. After that, we need to find which of the car is the fastest. So we need to perform the simulation. What does it mean? We need to simulate for each car the behavior of the drivers. So we start with the turbo boost speed activated for a certain amount of time. We need to perform step-by-step advance in the track. and we need to find the times needed to complete and to reach the finish. So we perform another for loop and we do this. So simulate for each car the driver behaviors. So we perform another for loop in page C. Okay. And of course, we need to store before not only the current winning of the track, because we analyze the solution step by step. So we need to find the current solution at each step. So car winning. This is the identifier of the winning car. And we need also to memorize the time of the best car. So we need also to store this in order to understand if the current car is better than the previous car. So this is the time needed for the current winning car. Okay. And at the end of the solution, we need to return to the function the identifier of the winning car. So we are in a single simulation. So we are a single car. We have all the information. We have all this information. Okay. And we need to find the required time for this particular car to complete the tasks. So we need to store another two variables. In particular, we need to store the current time, so current simulation time for this particular car, and we need to store the current length of the simulation. Reached length. Simulation. Okay, so we in this part try to simulate the step by step the driver. After that, we need to check if the current time is better than the time needed for the previous car. So at this time, what we have to do is to check if the current time, if we have the first car, we need to check if the car time is equal to -1. So this means that if you are the first car or better than all the previous one. Okay, so if this is true, this means that we are the first car, so we of course are the best so far. Or if the current time is less than the current winning car. Okay. We have to pay attention that if the current time is the equal of the car time, so if the current car needs the same amount of time of the already winning car, we need to return the first one. So in the last line of the promise statement, we can read that in case of tie, the driver with the low identifier is the winner. So we don't have to worry about this case. So we need to worry only about the first time, and if the current time is less than the best time so far. In this case, we store the current solution to be the best solution. So this means that car time will be equal to current time, and car winning will be equal to the current step, which is I. Okay. The last thing to solve this task is the difficult part, of course, but we need to simulate step by step the driver. So what we have to do in this part is to perform a while loop. In particular, we are interested to simulate the car unless we have finished the race. So this means that we have to check that the current length is less than the track length. So in this case, this means that we stop the simulation when reached the last meter. Okay. In this part, what we have to do is find the current speed. So we need to understand that we are the turbo boost activated or not. So the speed of the car at this step. Then we suppose we will find this later, of course. After that, we increase the current length by the current speed. So if you are at a speed of 10 meters long, we increase the current length of the current speed. And we increase the current time of 1 second. So this means increase the simulation by 1 second. And this means that increase the length by speed. We need to find this particular information. So at the beginning, we suppose that the current speed is equal to the C of S, so the speed, the normal speed. We need to understand if the car is running the turbo or not. This can be done by a simple calculation. This means that, let me open a comment here. So let me assume that we have a normal speed of 5 meters per second. We have a turbo speed of 10 meters per second. We have a cooldown of 3 seconds. And we have a duration of 5 seconds. Duration. Okay. This means that we have 5 seconds of turbo, 5 seconds of normal speed, and so on. And so, okay. So we can take this simulation in blocks of turbo activated and turbo not activated. So this means that we can see the simulation in step of cool down plus duration. So in step of 8 seconds. Each 8 seconds, the first 5 seconds will be with the turbo activated, and the last 3 seconds will be with the turbo boost not activated. So in these 8 seconds, we will start from 0. We have this part with the turbo boost activated, and 3 seconds with the turbo boost not activated. Okay. And what we have to do is to understand in which of the current seconds we are. So let's assume we are in the time number 50. Okay. And what we have to do is to perform the remainder of the integral division. So we subtract a number of time unless the number is less than this amount, in order to understand in which we are. So this means that, for example, we have to perform this operation, -8, and so on. So this is called reminder. So we have to perform this operation. You are familiar with programming. And this is equal to 2, because we have this particular, okay, which is okay. And okay, this means that we have in the second of the simulation, and this means that the turbo speed is currently activated. So how can we transform this into coding? So what you have to do here, so I will remove this comment and Press it here. Okay. Okay. We are asked if, so we will take this sum, which is C of C plus C of t. Okay. Step duration is equal to t. Duration of turbo plus cooldown. And we have to perform this operation. So if we are turbo boost cooldown duration time, so if the duration of the turbo speed is less than the current time with the remainder of the step duration, this means that we are in the step where this turbo speed is activated. So this means that the current speed is equal to C of t. Okay. So this is the difficult part of the task you need to understand in order to simulate this faster. And we will try with an example. We will see that there is no bug in solution. So we will pass to the first task. Okay. We have already here a solution, and I have prepared some input files and some output files. And we can simulate it first with the problem statement example. So we can perform this. So we have two problem statement. We can do one. So we have the first one, which is 22, 0, 3, 5, 2, 1, and 1, 1, 7, 4, and 6. Okay. So we have a bug here. So the bug is here. Okay. I forgot to increase the code length. So we will repeat this step. Okay. Okay. The number is returned 0, which is not correct according to the problem statement. And we try to understand by comparing to the solution. So we perform some printing in order to understand the behavior of the competition, of the car competition. So car with identifier I, step time, length, current length. Okay. And we will compare this to the solution in order to see if everything is correct. Okay. So we can see that the first car is the solution of the first car. We have okay, so the bug is in the first step. So the first step we had that the car will reach 5 meters. We have here 3 meters. So we are considering the normal speed instead of turbo speed. So we can do this by so the bug, I suppose, it here. So this the bug can be here. So better put some parentheses in order to be 100% sure. Okay, so speed here. Okay, current speed is this number. And as we can see, okay, so the turbo speed is activated one notch. Okay, 2 seconds of stop and 1 second of turbo speed, 2 seconds of stop and 1 second of turbo speed, and this is not the correct behavior. So we have inverted the current speed. So I have a solution. Okay. Current length. Okay. So one skills in order to win a competition is to perform debugging in real time. So don't expect to write the correct solution at the first try. You need to understand how to debug and to find the solution. So okay. So the current time. Are asked if the current time is modulo step duration is less than the time of turbo speed. So this is the number. We are looking for this number, duration time, C of t. Okay. Okay. So if the current time modulo step duration is less than the duration time of the turbo boost, we are currently in the turbo boost activated. So, okay, try this one. Sorry. Okay. So I suppose we have the correct solution. So step 1, 5 meters, then 8, 11, 16, 19, and 22. And for the second car, 7, 14, and 21. So this is the correct solution. Try with also the second test case. We will try. Okay. And for the second case, the solution is correct. So this is the solution for the first task. It's simply enough to simulate step by step the behavior of the car. The difficult part is to understand the current speed of the car at each step. So this can be performed with this solution. And I suppose if you haven't any question, we can pass to the second task. So this was the easier one. Okay. The second task is called slot machine. So the statement said that we are in a casino with an initial budget, and we have a set of slot machine, and each slot machine costs a certain amount of money, but will give us a fixed winning price. So our goal is to find the fastest way to reach a certain amount of budget by playing all of these slot machines. The fastest solution is to play at each step the slot machine that increase the budget in the better way possible. So we will pass again to the problem statement in order to understand the requirements. So we have an initial budget of B of I, so we with a set of money available to play the slot machine, and our goal is to reach a budget of B of F. So we need to try to reach this budget, which is of course higher than the initial. We have identified a series of slot machines, so we understand that by playing a slot machine, we are 100% sure that will give us a price. And in particular, we have n different slot machines, and each of them requires a cost of C of I, which is subtracted from the current budget, of course. And this slot machine will ensure us a winning of R of I money. Of course, as in the real case, we cannot play a slot machine if the current cost of the slot machine is higher than our budget. So if I don't have the money, I cannot play the slot machine. We can play unlimited number of time each of the slot machine, so we can use every machine any amount of time we want with an unlimited number of times. But we need to find the minimum number of slot machine play in order to reach the final budget. So we need to maximize the budget in the less time possible. Let's pass to the input data. So in the input data, as before, we have a number of test cases as before. Each test case will consist in a line containing the number of slot machine, the final budget, and the initial budget, and different lines with the information of each slot machine. For each slot machine, we have that the number COFI is the cost, and the number of ROFI is the reward gained by playing that slot machine in particular. The solution in this case is pretty simple, because we need to return the number of slot machine games, not the configuration, but only the number of rounds needed to run to find the final budget, and that's it. We have some constraints, so this is a little bit difficult than before. We have 10,000 different slot machines at the worst case. We have 1 billion in the initial final budget at the worst case, and we can have a total cost for each slot machine and reward of 50,000. So these with the numbers so high, so we have budgets of billions of money. It is not possible to simulate step by step, but we need to optimize the solution somehow. So again, we will open up the solution, and we have the problem statement by your side. As before, we read the input data, simulate and find the solution, and return the solution. In this case, the solution is the number of turns. So we will start, of course, by 0 turns, and we will return the numbers. So pretty simple, the beginning. Again, we need to read the input data. So as before, we have N, B of F, and B of E. So we perform the same operation as before, map to integers the number in the current line. So input and split by space. Okay. We need to read the slot machines info. So for each of the slot machine in range, the current slot machine info. Okay. Again, as before, we need to store this information in an array. So we create an empty array machine. We read the cost and the reward in 2 different integers, cost and reward, and we append these 2 numbers in the machines array. So C and R. Okay. We pass to the core of the solution. We need to simulate step by step, but with some optimization. So we will try with a simple solution. We need to optimize it. We will see how this performs with the big input file, and how we need to reduce the running time. So as before, we need to start with the initialization with the context. So we have the number of turns equal to 0, but okay, we also need to perform iteration. That means that while the current budget, so while the budget, so we set the budget to the budget initial, so current budget is equal to the initial one, the number of slot machine turns, okay? And while the budget is less than the final budget, we perform the simulation. So this is our while loop as before. What you have to perform here, so the solution is, the simple solution is intuitive, so we need to find the available solution, the available slot machine, and we need to find which of the slot machine increase our budget the most. So we need to find the one with the higher difference between the cost and reward among all the slot machine. And we have to find this by iterate all the slot machines. So for example, okay, so here we increase turn by 1, so increase turn of 1, and we need to find the current best slot machine. So what we have to do is to save the best slot, the ID of the best slot machine, so again equal to 0, okay. We iterate over all the slot machines, so again for of I in range of n, okay. And we ask that if the cost of the current slot machine is higher than the budget, this means that we cannot use it because we don't have enough money to play it. So if machines of I of 0 is greater than the current budget, continue. So this means this machine is too expensive, leave it. Okay. And at this step, we need to understand if the difference between the reward and the cost, which is the increasing of our budget, is higher than the best slot machine found before. So we need to understand in advance that if the cost is less than rewards, of course. So if the cost is greater than rewards, this means that we can have some slot machine with the rewards which is less than the cost. So this means that if we play this slot machine, our budget will decrease and not increase. So we of course skip this particular slot machine. Okay, and if this is the first available slot machine, save it, but this is of course the best. Okay, so best slot machine is equal to I, okay. And at this step, we need to understand otherwise if this difference, so the reward minus the cost of this slot machine is greater than the best rewards. So we create another variables, best rewards here. Okay, we store these not only with the index of the best slot machine, but also with the best indexes. So we will store this value in the best rewards variable. Okay, and okay, if the current reward is greater than the best rewards, we will do this again. So this is the best solution. This can be optimized, of course. So this can be transformed only one if. So we can do this if the best slot machine is null, or the current slot machine has a greater reward than the already seen before. Okay. At the end, so at this step, we have found the best slot machine to play. What we do, we increase our budget by the difference of the cost reward. So we can perform this step by step. So we this, for example, best slot machine. Okay. We play the slot machine and we gain the price by increasing with the rewards. So the rewards of the slot machine. In this way, what we do is to at each step play the best slot machine that give us the higher rewards as possible. So this means that after running the solution, we found the minimum amount of turns needed to find the solution. We try to understand if it is correct by running the solution over the problem state, the input in the example. So again, yeah, okay. Solution. Okay. Okay, it is not still correct, so we need to understand. Okay, we compare this with the solution in order to understand where the bug is. And what we can do is here, again, print as before, so turn is equal to turns. So the budget is equal to budget. Okay. And we can print the index of the best slot machine and the rewards gained by playing it. So we print this for slot machine. Okay. Okay, I think we have already see the bug. So the bug is this. So best slot machine is equal to -1. So this should not be happens. So this means that this code is never reached, which is not possible, of course. So the bug can be here. So the first number means the cost. So you can skip it. Okay, no. This means that the cost is greater than the current budget, so we skip it. Okay, and the bug can be, I think, here. So this means that the machine. Okay, this means that the cost is less than the reward. So I think that this is not correct. So this is, I think, the solution. So we swapped the cost and the rewards in the checking the final amount of money given by a single slot machine. We can run again solution. Okay, so the solution is 21. So this is correct. Okay, so we understand that we start with the slot machine that give us a reward of 14, then we pass to the slot machine that give us a reward of 19. The solution is correct, but if you use this during competition, we can see that the solution is not properly optimized, because I can show you in this case I have prepared several input files. So I have input file of increasing difficulty. So I can run the simulation, the first input file, and the solution is instant, okay. The second again is okay, the third is okay again, the fourth is much slower than before, and the last test case, as you can see, is very, very slow. And what can be done to optimize this part? So of course, if you wait a certain amount of time, we can reach the final solution, but in the challenge, you only had 4 or 3 different menus. I don't remind correctly, but this is not enough to solve completely the challenge. So I will leave you simple remarks in order to try to solve the solution by yourself. And the solution is that the one possible optimization is to reduce this part. So as you can see in the previous example, the best slot machine is always the same after one step. And in particular, the best slot machine doesn't change too much, and this can be optimized. So for example, we need to find this number once. So your part can be done if you are enough skilled to try this at home, is to try to reduce this part in order to find only once the best solution. And that's the solution. So if you are writing this using a more efficient approach, it will pass the evaluation in the platform. And that's it. This is the solution of the second task. And I think it's, and that's it. So let's do a brief recap. As before, we have another simulation. So let me pass here. Okay, we have another simulation task, but this time we have to choose something. So in the first task, we have a solution, line 30. Okay, yes. And in the first task, we have a simple simulation problem where we doesn't have to perform any choice. So we can simply simulate and try to find the best solution. This is another simulation problem, but we need to perform a choice. So we need to find the best slot machine. This can be done with a greedy approach. So this means that at each step we take the best slot machine available among all the indexes. And this is slightly difficult than before because we have to perform this kind of check. But besides this, the approach is the same as before. So pass to the first and I think the last problem of today. So the first task is named flowers. And in this task, we have to help a farm that has to plant a set of flowers in a field. In this field, we need to plant the flowers as far as possible. We need to find the maximum distance for the flowers, meaning that some cells in the field can contain rocks. So you cannot plant flowers on the rocks, and we need to find an assignation on the fields in order to maximize the distance between all the flowers. For this kind of task, we need to perform a clever idea is to doesn't try to find this directly the solution, but we need to simulate again the planting of the flowers, and we need to write a function that given a fixed distance. So let's try with a solution of distance 2 with a distance 4. And we need a function that returns us if it is possible to plant the flowers on the fields. Once we have this kind of particular solution, we can use a binary search approach in order to optimize the solution. So this is what is called binary search over the solution approach. and can be applied to a different amount of problems. Let's pass to the problem statement again. Okay. So this is more mathematical than before. So we have some formula on the problem statement, but this doesn't mean that we need to scare it because it's very simple. So a farmer has to plant a number of flowers in the field. The flowers must be placed as far as possible, and we need to find the optimal distance between the flowers. So the field is a simple rectangle. We have a rectangle of W times H cells, so can be represented as a grid. And some cells of this grid can contain rocks. We cannot plant flowers on the rocks, but all the other cells are available. We know that other cells in the fields, in particular G cells, are available and we can plant flower in them. For this particular task, the distance between the flowers is calculated according to the Manhattan distance, which is a famous approach to evaluate the distance between 2 points. Usually, we use the Euclidean distance, which is the common distance we use every day. So it's the distance between 2 points. But in the Manhattan distance, the distance is evaluated as the difference, the absolute difference between the 2 coordinates of the 2 points. So this is the Manhattan distance of 2 points, 1 and 2. So it's the absolute value of x of 1 minus x of 2 plus y of 1 minus y of 2. And the flower distance for this particular test case is evaluated as the sum, as the minimum sum of all the pair of flowers. So we need to place all the flowers, and the solution is the minimum amount of distance between all the flowers. So this is the definition of flower distance. Our task for this challenge is to find the maximum flower distribution distance between all the flowers that guarantees the possibility to plant in the fields. So we need to find a configuration of the flowers over the fields that maximize this distance over of the flowers themselves. Again, in the input data, we have some numbers. So we have the size of the grid, the number of flowers, and the number of patch of the fields free of rocks. So the cells where we can put the flowers. And then we have a set of lines containing the coordinates of the patches available to be planted. And for this task, the coordinate starts with 0, and the upper left coordinates is 0, 0. For this is pretty common, pretty standard in tasks. The output file, once again, is a number, which is the distance, the maximum distance, and it is all the information required to solve the task. Let's see again one problem. So we can see that the grid is small, so it's not so big. We have a grid with the size of 150 by 150, and we have a maximum of 50 flowers to put on the field. So the numbers are very low. So we need to find a solution considering these lower numbers. Okay, so this is the input file. So we have a 5 by 5 grid. We have 4 different flowers to plant, and we have 15 different patch available to be planted. So this is the grid corresponding to the input file in the example. And as you can see, one possible solution, this one, because in this case, the minimum distance between a every couple of flowers is equal to 4. So this means that no flowers can be placed with a distance of 5 or higher. So the solution in this case is 4. This is a configuration of the best solution, but it doesn't mean it is the unique one. So our goal is to find a possible solution that maximizes the minimum distance, and that's it. We can pass directly to the solution again. In this case, okay, we have, okay. Once again, we can read the input data, return the solution, okay, simulate and find the max distance. Okay, in the input file we have the first line containing W, H, F, and G, which is equal to map of integral numbers of input split by space. Okay, so as before, we read 4 different numbers by mapping them into integers. We need to store the patches and reading them in the input file. So again, for in range of G, okay. For each patch, we have the coordinate x and y. Okay, coordinate x and y. Okay, and we can store these in the patches array. So x and y. Okay. We're finishing the reading of the input data. Okay, and we try to solve this problem with a different approach. So we can write a solution in this case. So suppose to have a solution, suppose to have a function called canFill. canFill is a function that given a set of points, accounts and a distance, find return true if we can put points on available spaces with a distance of at least distance. So suppose we have this kind of function, which is called an oracle. So we suppose we have already written the solution that answers a simple question that we can fill the field with flowers by maintaining a distance of a certain amount of space. Okay, so we will return to this later. So to write this later. Okay. Once we have written the solution, what we can do is try step by step. So, for example, the solution at the beginning is equal to 0. Okay. And what we can do is while we can fill the fields, so the patches, with a solution is equal to solution plus 1, increase the solution. So what you can do is this. Start with a solution of 0, try to increase the solution 1 by 1. So this means that try to increase the solution of one space. If this can be performed, and this is the answer returned by the can_fill function, and this function continues to execute until this is not returned false. So this can be performed, and we are assured that at the end of the execution, we have found the maximum available space, which is also the solution. And this is the number returned. So at this step, the only things remaining to perform is to write the can_fill function. And one thing before, so we need to evaluate this particular function. So define the Manhattan distance. Okay. Manhattan distance within point A and B. Okay. And as I said before, the Manhattan distance between 2 points is the absolute difference between the 2 coordinates of the 2 points. So P of A of 0 minus P of B of 0, and again with the Y coordinates. Okay. And at this point, we need to implement the can_fill function, and I remove this. Okay. We assume that it is not possible. Okay, and we start with some base case. So this is a recursive function, and if the count of points to be put is equal to 0, we of course return true. So flowers to be put is equal to 0. So of course, if we don't have any flower, the solution is always correct. If no space is available, return false. So if the number of flowers is greater than the number of available points. And then what we can do is to try to put the flower in each of the available points. So what we can do is to iterate. So we can do for E in range of each point. So we try to simulate this one. Okay. We take the coordinates of the current points of X and points of Y. Okay, is equal to points Y. So current points. In this step, we try each possible points. Okay. We try to simulate, so we are supposing at this step we put the flowers in this point, and we need to find all the available free points to be put the next flowers. So we need to find the next point. So at the beginning, the next point is equal to all the available points, but we need to filter these to remove we need to remove all the points. Okay, so we take only the next following points because the first one will be not taken accounts. And we select these points for X and Y. Okay, if these points is less than is not in the neighborhood of the current placed flowers. So, so this is the list of pages with enough distance taken into account the current flower. Okay. The next point in this case, we need to filter. We can filter this. So we have to filter if x is equal to distance. Okay, so this means that this is over the grid, or once again, distance. Okay, and we can do this also for the other coordinate. Okay, and at the end we need to check if the Manhattan distance, which is this, between this point and the previous point is greater than the given distance in the function. Okay. Okay, that's it. So this is the array containing the points available for the next step. So we put the flowers, we remove all the patch that is not longer available because the flowers will be otherwise too near to the equivalent points. And this is the tricky part because we can we have to perform a recursion call by checking if we can fill the patches by considering the next points, by removing one of the flowers, and with the same distance. So that's it. If this is true, this means that the solution can be the solution is valid. Okay, and this is the solution. So the solution works in this way. So we try to step by step to increase the solution with a function that, as well as if it's possible to place the flowers with the amount of distance, and the solution, which is the function can fill, considers all the case that, for example, we don't have the flowers, we don't have the available space, but is the important part. We simulate by placing the flowers in each of the place and try to iterate in order to find the solution is valid or not. And try to see if this is correct, or why we debug it. Okay. We print. Okay. Okay, there is a bug, so we'll try to debug this in the last minutes. Okay. So, okay, this is correct, of course. So the distance is correct, the patch is correct. Okay. So the number of available is equal to 0, we return true. Okay. Line 51 in the background. So this means that we simulate step by step the solution. We have these available patches, and we have the number of flowers, and we have the solution. So this means that we increase one by one the solution, and this return false where when the solution is not valid. So okay. Okay, so the bug can be here, I suppose. So the distance is valid, is not valid if it also is equal, because we need to add also the distance if it's equal to the fixed distance, of course. And we repeat this. Sorry. Okay. Okay, so the solution is correct. So as before, this is a valid solution, but is not optimized one. And we can see by simulate with one of the input file in the competition. So I have once again several input file of increasing difficulty according to the round one according to the competition. So we can see that the first solution is fast, for the second solution is again fast, and for the 4 is fast again, but for the last, okay, no, it's pretty fast again. So this is enough to solve the challenge. If you want to implement, to optimize the solution, one thing that I leave you to homework is to try to implement a binary search to optimize the solution. And what we can do, for example, is to fix a starting and ending point, and we can optimize the solution by reducing the number of calls of the function count field. So this function is pretty slow because it's a recursive one and perform a lot of operation. And for bigger and bigger case, it does not behave efficiently and can be optimized by reducing the number of calls we perform on the function itself. And to drive this, we can perform, of course, a binary search, but we can also use what is called a exponential search. And I'll leave you this for framework if you want. And we are almost out of time. So if you have any question, this is the last minutes available. These are the solution of the first 3 problems for the Quite challenge. And if you can see the scoreboard, I suppose this is enough to be placed in the first 50, 100 teams. And I think that's it. If you have any question, we are available again.
Yes, thank you.
Yes.
Thank you so much, Gaspare, by the way, for this training session. Again, as Gaspare mentioned, this is the right moment if you have any other questions or doubts about these 3 problems. Maybe Gaspare, in the meanwhile, we can take the chance to give a couple of useful information. For example, here, all these problems, you can find all these problems in the training section of the website of challenges in sandbox mode. So guys, if you would like to keep training and see how well you can score after following this video, you can do it. And of course, this video will be available for you, both for the internal communities of repliers listening to us today, and for the external communities on YouTube. So these are 2 main information you can take note of. Thank you again, Gaspare. By the way, you are a member of the Codemaster team who is already working on the next year edition, the 2024 one. Another important thing to say is that we would like to share with you a feedback form, because it's really important for us to listen to your feedback. And we hope that this session has been useful. And we hope also, Gaspare, maybe to offer other sessions like this in the future to help getting ready for the next edition, right? I think it could be a nice.
Yes, of course.
Yeah.
If you are in the Discord server, you can ask us questions, I remind you. So the Discord server is a Discord where you can find all the authors and interact with all the participants. And if you have any doubt, you can ask us some question on the available training channels.
Yes. So unless we have any other questions, but I guess no, it's time for a goodbye. And again, we hope to see you very soon in the next training session like this one. Please remind to fill the feedback form we are going to share with you in the chat and via email. Thank you so much, guys, and
thank you, everyone.
Thank you, Gaspare. Bye.
Bye, everyone.